All right. Happy Saturday, students, class. Thanks again for the feedback to start publishing these videos on Saturdays in order to give you time to review and digest stuff on Sundays and a little bit on Mondays. Knowing your schedule really helped there. I wanted to continue our series on parametric and performance modeling based on feedback we discussed in class around starting scripts from scratch. And we had a good introduction to that, walking through the example where I showed you how to make a generator. And now I wanted to do the same thing, but covering the evaluator side, or what performance metrics I was able to get out of that example file. So super quickly here, just kind of going through, oops, the rest of the presentation. High level reminder, we're putting together these three pieces of technology. Right now we are putting real-time rendering a little bit on pause, just so that we really get these two elements down here working well. And again, we're trying to actually do a direct pairing for experiment X, where you would use a genetic algorithm to optimize a design that has a generator and an evaluator. So we're focusing in on this spectrum, or this end of the spectrum of the three pieces of technology. And super high level reminder, we are geometrically constrained by what can and cannot be accomplished inside of Rhino as our kernel. We're using visual programming to create scripts or definitions, and we will leverage some other plugins as we need to extend that capability and capacity to get closer to actual landscape modeling needs. And later today, I will show you some LandKit Pro features. So what's this video going to cover? I'm going to just review the generator elements, but today is really, or this video rather, is really focused on Evaluator, how to build them from scratch. So these slides are a lot more focused just on the Evaluator, but there's a little bit of a review of the generator approach. And again, my approach always is plain English, pseudocode. What are you trying to achieve? What are your sketches that might accomplish that? This is all very analog to begin with. And once I feel comfortable here, that's when I start jumping into some Rhino sketches just to get my bearings, and then finally Grasshopper. So let's walk through that same example. I'm just gonna zoom back out. This was this concept for the Friesenhahn cave, this idea of having I guess we'll call it a cave campus, these series of buildings that would go around the cave site that had a special protection zone, and to basically allow the computer to decide where to place those separate buildings as a campus, how big they should get, where along the offset they should go, etc. And a big aid for me and my teammates at the time making this sketch was to actually leverage the synthetic working sheet, just as a place to remind ourselves what it is that we're trying to do in an extremely step-by-step fashion. So if you remember from my brief lecture in class on how this project came about, we had a list of requirements and some themes about what the project was trying to achieve. And we really, again, as a major theme, we're trying to emphasize the idea of boundary and threshold, from deep time in the cave to more immediate time with the suburbs. And the way that we had imagined putting the campus into life, this concept, was to actually just take each of these requirements of square footage and imagine them as series of bubbles or circles, like literally that were around that same size, and to place those bubbles down. Now, we didn't predefine how big they are when putting it down. We wanted the algorithm or the script or the definition to design spaces, and then we would programatize the spaces after the fact. But generally, the idea was to take these circles of space or area and put them on the site in a intelligent manner and letting them respond to that special protection zone, creating that threshold and boundary condition. So, again, I always love to work with sketches. This was a graphic shorthand representation of the base site. This is that square, and around it was the suburbs. The cave is here, and this kind of almond shape or bean shape is that special protection zone. So we knew that all of our program bubbles or circles must fit inside the site boundaries. It can't obviously step outside. We wanted it to be oriented to the SPZ. We wanted to intentionally create bubbles that followed this because we thought it was an interesting constraint and we thought we would play with it. And we wanted the bubbles to move relative to their position around that special protection zone. So they could move. And we wanted the bubbles to grow and to shrink. We wanted it that when they crossed this special protection zone, they would get cut or trimmed. And that trim would create a threshold, a kind of window or entry or view looking straight towards that cave entrance. Now, for more conceptual reasons, while the windows looked into the cave, it was intentionally creating this kind of isolation from the suburbs, a bit of an intentional block to carve things out a little bit away or focus the attention of the occupants towards the cave. And then you could use those entryways as ways to generate paths, connecting them together, and obviously leading you towards the cave itself. Now, as a bonus feature, we thought, it would be nice at some point to look back out of deep time and into our contemporary time. So we had these, we designed balconies, and I'll show that in another video, how we had these balconies that would look back at the suburbs and at the same time could let you look back into the site. So the approach, as was mentioned last time, is taking those sketches and taking those descriptions and starting to plot them down into Grasshopper. And the way that I've approached things from scratch is to take those words and those intentions and those sketches and then starting to build backward from pieces that I intuitively know as a designer. So if I know I want to make a circle, I will pull down a circle component and then work backwards and figure out what is it that I need and want to construct a circle parametrically. So generally speaking, that covered the generator side of things. And I showed in last class and in last video how to approach that. But what I didn't cover and what I want to cover in this video is things that would basically guide that generation towards specific objectives. And in this case, I'm calling objectives goals. So excuse my flipping between language here, between objectives or goals or metrics. In some way, they mean very much the same thing. I'll explain why. But I did want something that would cause the bubbles to grow. So there was something really neat about them being cut by that SPZ and how they would create this big kind of window face. I thought that was really neat. And so we wanted to encourage that. We wanted to increase the bubble sizes so that they would try to get cut. That seemed cool. But at the same time, we didn't want them to just grow all the time, because what that would mean is that they would always get cut. And we wanted some variety in the end result. We wanted to mix and match our results, because we also like that not all of the bubbles were treated the same. So we needed a goal that would cause them to grow, and at the same time, a goal that would cause them to shrink. And in this way, these two goals were directly competing. And again, genetic algorithms work really well when they are looking at a problem of direct conflict or competition, because you as a designer, as a human being, can't foresee what a good result will be. But a genetic algorithm can learn what a good result could be. And then you play the role of an editor. So the other thing we wanted to do is that we wanted to create bubbles that would cluster together. We thought that was neat when they started to form little blobs. It seemed graphically and spatially more interesting. But we knew that if we just maximized that it would just create one gigantic blob. And so we were like, that's probably not what we actually want. What we actually want is some sort of composition of bubbles coming together, but also having some variety where some get pulled apart. So those were our two ideas. And again, these are directly in competition. And as such, a genetic algorithm is going to be really good here. So we wanted to think about what kinds of goals would help rationalize and help guide these movements. So for growing the bubbles, we really thought it was, again, this is a design intent. It's tied to an atmospheric and sustainable desire of creating more natural light within the closed structures. So again, if I'm making these kind of circular enclosed buildings as little caves, I'm cutting them open and allowing natural light in and allowing somebody to kind of look out into that forest and back at the cave and maybe remark that it's really nice experience. So how would I measure this? I have an intention, I have an idea, it's going to be in competition, it sounds really neat. Well, the measurement for this, we wanted to make it really simple to start. And we were like, what if we just measured the total linear meters of the trimmed bubble or circle, which could represent a window? It's like, how long or wide does that window face? That's what we were interested in doing. And here's a little plan view. Again, here's one of the bubbles coming down. It's trimmed by the SPZ and it makes a window. This was an objective that we wanted to maximize. We really liked this idea that it would create so much natural light and create this great view into the forest. And so we were like, we want to tell the genetic algorithm, hey, you want to maximize this. And it was a qualitative, it started as a qualitative goal. It was an experience of light, but it was very easily turned into a quantitative goal because it was just measuring it by how long this particular line is. So now I have a plan. I know I want to find the length of this line, and I know I want to maximize it. So now what would cause the bubbles to shrink? Again, we don't want to just let them grow infinitely. The rationale that we had here is that not all bubbles can grow infinitely large. We just didn't want all the bubbles to grow, even though it would create that cut condition, and that was cool. We just knew that it had to stop the bubbles from growing infinitely large. And this was pretty easy. This was like a sanity check that we have a maximum limit of square footage. The design competition was in square feet based in America. And so there's a limit to how big the bubbles can grow. And so the rationale here was very easy. Let's just stay within limits, and let's make sure that we are not, it was kind of like breaking the bank if we were thinking about a real world constraint here. So how would we measure this? All we wanted to do was measure the total amount of square footage of the area that is actually planning on being built. So not the total circle size, just the circle size that is trimmed and contained outside of the SPZ, or special protection zone. This goal was a constraint in the sense that anything too big is not useful for us. Yes, we can go a little smaller, but ultimately we're trying to constrain this goal to be like, hey, just give me the results that are big enough and hitting this target of square footage. And this was a very easy quantitative goal. It's just a cap on how big it is by a measure of area. Next, again, we wanted to push the bubbles close together. We really like this condition, and that was a design intent, but it was also a design intent from feasibility. So this goal came from a stakeholder imagining a construction team on site doing these. We had imagined that the bubbles would be made out of 3D printed earth that was found locally. And so we were like, this goal could really be around an element of constructability or feasibility. Having bubbles closer together means that there's less unique foundations and the crews need to move around, which ultimately means, let's focus on quality over quantity. And let's not just make foundations just willy-nilly. Let's make them where they really matter. So this metric is short form for measure, is basically, I want to count the total amount of linear meters of wall, assuming we're 3D printing concrete, or in this case, 3D printing earth. So I want to count these walls, the length of these walls here. Again, this is a little sketch. Sketch matters a lot. What am I trying to achieve, even just in drawing form? And I want to count these, not these walls, because those were the glass window walls from before, but basically every other wall. And my goal here is to minimize this. I want to try to reduce the amount of 3D printing concrete or earth that's on the site. I'm trying to reduce the amount of material and labor and unique foundations and cost in order to actually just make a quality project. Now, this goal is a mixture. It's more on the qualitative side. It's a perception of work and a perception of complexity. I just am trying to take this idea of construction and feasibility and boil it down into something that is very, very measurable. And the last one was, if that's pushing the bubbles together, what's pulling the bubbles apart? What's making them look a little more interesting? And this one was an even more qualitative aspiration. This one was basically trying to get a mixture of building or little pavilion to tree ratio and views beyond the site. So again, this inspiration image was really helpful for me. And this was made in Midjourney. We were just kind of messing around. And we were just like imagining these different pavilions that had these glass faces and were kind of curved inward. It was a different geometry at the time. We were imagining different construction techniques. But we really like this idea of like a mixture of views where you can look at other campus buildings, but you can also look into the site, again, back at the cave. And it's a little shielded from the back of the site where the suburbs were. So this metric was a little more complex. We had to think about this one actually quite a bit. This one was that we wanted to measure the linear meters of a view cone. And we specifically used a tool called an isovist, which comes out of the box in Grasshopper and is a very common technique these days to measure views and view cones and complexity or area of views in general. And we wanted to measure how long this view cone is. And the idea here is that if there are more breaks, more buildings that kind of break up the view cone, it will create a longer value. So the idea here is that we want to maximize this number. It is increasing the visual complexity of the site. Now, this was very much a qualitative goal. It was this intention of getting a variety of views and view quality, but it could very quickly become a quantitative measure by measuring linear meters. So again, a goal might start as a kind of floofy, floofy is maybe a bad word, more fuzzy, qualitative, aspirational, feeling-based metric. But it can kind of quickly turn into something measurable, depending on how you approach it. And again, these were put down into our generative thinking worksheet as a place to remind ourselves where we are mixing the generator and the evaluator together. And it was handy to keep using this worksheet as a place to return to just check if what we're saying and what we're sketching and what we're trying aligns with our larger aspirations. So let's take a quick look at how these were actually made. So I'm just going to turn all this off, but on the right here is that same file, and you guys have access to this file, how to approach scripting in Grasshopper. It's the same O1 file from a .3dm or Rhino file. And this one, I've made a couple modifications to the script that I shared previously, specifically for these evaluators. And I just underscore this as version 2. So I'm going to turn this off. This is what it looks like in the end. Just turn these off. Now, again, just a quick recap on the generator side. These were my 6 steps. I wanted to offset the SPZ, create bubbles at their start positions that go around, change their diameters, be able to basically change the diameters for real world values like meters, how big are they getting. This was to be able to essentially make the circle. So while I had a directionality and that directionality had meters, I wanted to now make a full circle. And then finally was to join them together if they merged, and then trim them against the SPZ. And those were all pulled down into these clusters of components here. Each of the blue signs just says, turn me on to see the end result of this intention, the pseudocode. So now we're going to do the same. We're going to do the same with our evaluators. In my slide deck, I indicated 4 competing goals or objectives. The first one was calculating light openings. It was a measure of length. So I needed to calculate the total or the aggregate, because we want to combine many units together, of linear meters that are trimmed by all the bubbles crossing the SPZ. And this is something we want to maximize. So I did that for each of these 4 goals. And then what I did is copy these down here and start to figure out what components are going to help me achieve this statement. So let's go through each of them just for clarity. If I want to find, I'll turn on, here are my trimmed bubbles in the end. And I'll just step back and show you again that they are parametrically controlled here. Here they are moving along the SPZ offset. Here they are changing in their diameter. And they are getting trimmed and combined together in step number 6. So this resultant trimmed bubbles is coming out of that last command that we talked about, this kind of Boolean operation found under the intersect ribbon tab. I'm cutting a shape with another shape. So these are the curves that I have together here. And I want to be able to say, cool, what I want to do is if we recall our sketch here was to calculate just this edge, the length of the window line. So that's what I need to try and achieve here. And to do so, I used another intersect. This one was intersecting by region. So I'm trimming objects with other objects. I want to trim, in this case it says trim a curve with multiple regions. I want to trim this curve with each of these red, here they're colored red, but they are my buildings. So I want to trim this line from these lines and just get this line. There's many ways to do this. This is just how I approached doing it. But for this command or this component to work, I need to give it a curve to trim. I used the original SPZ as a referenced in curve. It's just pulled in from a container. So here's that curve. That's what I'm putting into C here. And then it says, give me the regions that you want to trim against. And for this one, it was my 6 bubbles. Just these 6 here from an earlier step. So I'm recycling an older component in order to achieve something new. And I'm going to turn that one off because the result here is as follows. These curves here, they're a little hard to see, but they are basically this SPZ cut by the bubbles. So now I have what I wanted. I've been able to achieve my sketch. Here's the line that I want to get. Perfect. How I got there doesn't matter too much. What matters is that you get what you wanted out of your sketch. I could have done this maybe a few other ways. This is just how I approached it in this one instance. Now remember, now that I have these lines, cool, what do I want to do with them? As a reminder, I want to calculate their linear meters. How long are they? Well, this one's pretty easy. There's a component that will measure something for you. You know, in Rhino, if you wanted to ever do this, you would just type in the length command and it says select a curve for me to measure. So I could take a circle here and say length, click on it, and it says, hey, that line or that curve there, it's 38.639 meters. Cool. The length component does exactly that. It's like exactly the Rhino command, just inside of Grasshopper. So now I'll just pull out a panel here to show you what it's giving me. And let me do this before I flatten it, because I think this is a key concept. When I do this, what do I get? Let me turn on these guys so that you can see what is being created here. I'm getting a list of 1, 2, 3, 4. 1, 2, 3, 4. I'm getting 4 values that are getting cut by the SPZ, which is good. That's what I want. It's giving me, hey, this curve here is 12 meters, this one is 16 meters, this one is 16, and this one is 16. Cool. But remember, what I care about is getting the total number, total values. So in order to clean up this way that this has been structured, you can see there's a lot of unnecessary tree structures. There's like so many references for just 4 types here. I actually don't need this structure. This dotted or dashed line indicates that there's a list of lists. I don't need that list of lists. So what I've done is I have flattened the result. I can right click and say flatten, or I can use the flatten tree, which will do the same. Give me the tree and the result coming out of this is as such. And I'll show you that these two do exactly the same thing. I have now planar curves coming out of it. Cool. And now that I have these, I can have a length. And I get 4 values. The same thing is happening down here. I have one list of 4 values. So this did exactly the same thing, just a curve with a flatten or a flatten before a curve or vice versa. They will create the same result. Again, what matters is that you're getting what you need. In this case, I need 4 values that I'm going to add up all together. And that's what mass addition does. Mass addition comes inside of the math ribbon tab. There's a series of what they call operators that basically do things like I want to add something, or I want to subtract it or multiply it. I want to check if it's larger than or smaller than. And there's these great ones here called mass addition and mass multiplication. Mass addition is one that I tend to use a lot for multi-objective optimization studies, because I'm trying to add all things together and get one value. In this case, I'm adding up all of the length values. Again, just for description, I'm adding up 12, 16, 16, 16 together in order to get a total value of 61.85 meters. I flatten the result just to double check. I just want to make sure that I only have one value at the end of the day. I'm trying to always get rid of tree structure when it comes to a final numeric value. And so I just pulled this out into a panel in order to just, as a mental reminder, this is the length of meters that I'm getting. And I could put this number into a number container, and I could have Galapagos, if we recall, treat this as my fitness value. It's just getting one number, and it can maximize or minimize against that. I'm just going to take that away. I don't need it anymore. And I just have a number container that I can use for objectives. Now, I added a component here. You may or may not have this plugin. It's called Human. Kind of ironic because most of the Rhino ecosystem is based on animals, and this one's called Human. This one's pretty neat from a graphic perspective. It allows you to create essentially custom representations of things inside of Grasshopper. In this case, I'm using the component called display custom line weights. So almost treating Grasshopper like Adobe Illustrator, what happens is that this says, give me geometry. It needs curves. It can do a few other ones, kind of sketchy style, but it's like, give me the color you want to shade these curves and tell me how thick you want it to be. So this is handy because you can see it just makes it pop out graphically on the page a little bit, or on the viewport a little bit easier. So regardless of where I move, this is able to, I can make these really thick, and now they remind me that those are the glass windows. Maybe to be even more didactic about it being glass, I could change these to being like a bright blue. And now I'm like, oh yeah, it's a window. So we did goal number 1. I just trimmed to get the curve that I wanted as per my sketch. I got it. And then I needed to measure their lengths and add them up to get to one value. And now I know I can either maximize this value or minimize this value. Let's go to the second goal. Much easier, I have to say. This one says I need to count the total amount of area. So this one was super easy. This one was, I need to calculate the area of the bubbles that are not trimmed away. So these pieces here, only these ones, I want to calculate the area. Well, again, I can go downstream, or rather upstream in my script and say, hey, these bubbles here in green are the ones that were trimmed and combined. That's exactly what I want to measure. There's nothing else I need to worry about. There is an area command inside of Grasshopper, just out of the box, that says give me area geometry or geometries, and then I'm going to calculate their area for you. Now I did a flatten at the beginning here. I'm going to just take a look why. Coming out of this resultant trim bubbles, you can see I have these planar curves or some circular curves, a mixture of different curves. And it's okay to have them separated out before, but I really don't need this tree structure to calculate area. So I flattened the result before getting my area. Again, I could use a flattened tree, totally fine. Or if I want to flatten something on an input or an output nub, I could just right click and say flatten or simplify or unflatten. So the area coming out of here now is a series of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These ones were blobbed together, 5 areas. And I want to use a mass addition to get one value, 789 square meters. Now, for my purposes, in this example, it was an American competition, so I needed to convert it to square meters. I just multiplied A, square meters, by B, the amount of square feet inside of a meter, to get to a final result. Not necessary for us. This was just for the competition itself. But just as a graphic aid, this was the area I'm calculating. All I did was put in a custom geometry node, after a surface and get a little color that I prefer, and basically just make these graphically pop out. Now, I also wanted to color these edges just so that it was a bit easier to graphically see, so that it was like a black line that I determine how thick or thin I wanted. Just purely graphic, no other reason. And I have my final value, area in square feet. I could again put this value into a number container. And I can ask Galapagos, hey, this is my fitness value. I want you to do something with this. Either you're going to maximize it or you're going to minimize it. In this case, we wanted it as a threshold. And so Galapagos will be not necessarily the best tool at this because it can only do maximize or minimize. So more complex goals, there's hacks for using Galapagos to do this, but we have other tools at our disposal. The third goal was calculate the total or aggregate length of all the walls that will be 3D printed. And this is something we want to minimize. So if I go back to my sketch here, in this case, we did the area, that was fine. This one was, oh, okay, we basically want to measure the opposite of the window walls. It was, I want to measure the length of the other pieces that were in there. And again, how we get this result matters to a degree, but it matters more that we actually get what we want. In this case, it is the length. We have to isolate these curves, just separate them all on their own, and then add them together, their length. So let's see how we did this here. Again, this was my approach at the time. There are many ways to do this. What I did was take the resultant combined curves, and I said, take all of these curves here, and I want you to explode them. Because I was like, oh, I think I just want some pieces here. So my approach was, if I was using a Rhino command to do this, here I have, let's say I join these together or trim them. Trim this guy. That's my cutting object from this guy. Great. I want to trim this guy from that guy. Great. And I now join these together. This is kind of the same thing that we have going on here as this. If I wanted to just get this curve, I would my gut instinct would be to explode this. I would use the explode command, and now I have these as separate line segments. So that was my approach here. Again, hand sketching is helpful, and then doing it inside of Rhino is starting to translate it easier. So I was like, oh, I think I want to explode this because I know I can get something to what I want here. So I'm just going to delete these away. So the explode command is found under the curve tools, the curve ribbon tab under utilities, explode a curve. It says, give me curves. You can recursively do it, which will keep trying to break it. And then it says, I will give you a series of segments, kind of like what we saw before, little pieces. And I was like, cool. I think that sounds like what I want. Then what I did is I pulled it out and I was like, I got some really weird results because they're being cut by this almondy shaped NURBS curve. And I was like, oh, interesting. What am I getting out of here? I'm getting a series of arc-like curves, ones that think they're close to a circle. And I'm getting planar-like curves, ones that are from a NURBS curve. It's planar, meaning it's flat, but it doesn't know if it's something else. And I'm getting a circular curve because here's one out in the distance that's not cut. So I was like, this is how am I gonna find just these ones? I want to get these ones, the circular ones, anything that's like an arc or a circle, but no planar ones. I don't want these ones. So this is where I used a special command that said, after I investigated what's inside of the curve parameter, I was like, hey, let me use a component called match text. Again, I'm reading this as a person and I'm like, oh, these are the types of things. And I'm like, if this text coming in from here, if it is reading as planar, this is the pattern I want to see. If it says planar, these ones, anytime it says planar, I want you to remove these. I want you to say, kick these ones out. So the gate not is basically a command that says, give me a list of things, and I will tell you whenever that is not being met. Oh, I thought it was bleeding for a second. When it is not being met. So here's what's coming out. It's saying, great, out of this list here, in each of these groupings, I have, this one is not a planar curve. This one is not a planar curve, but this one is a planar curve. So that is one that I want to get rid of. I can then feed those values, which create a series of true-false values. When is a curve true, planar, versus not planar? And I can say, using a way to get rid of data, how would I, this is a very also common tool, cull pattern. It says, give me a list of values, all my curves, and tell me the pattern that you want to use to get rid of things. So the pattern here is coming from if they match planar or not. And the result is that I only have arc-like or circular curves. Now there's no planar curves. None of these, only circular ones, which is, this is inherent to the geometry that I've made. So it's, this will be bespoke for each of you depending on how you build your geometry. But the result is that now I only have these ones, only the ones that are basically going to be 3D printed out of concrete or earth. And now that I have them isolated, I can again count their length or calculate their lengths, flatten that length list, and add them all up. And all I did here was just turn them on for a graphic representation. These were my 3D printed earth walls. So again, it has now matched my intention, my sketch. I've been able to calculate the total amount of linear meters, and it's perfect. This is exactly what I want. And again, I can put a number container in here now that I have just one number, and I can tell Galapagos if I wanted to use this as a fitness objective. I can maximize or minimize this. We are almost done. Fourth goal. Fourth goal here is that more fuzzy concept of composition. I want to pull the bubbles apart because qualitatively, I want a mixture of views and I want the bubbles to not just form one blob. So as a sketch, I was imagining somebody standing at the center of the cave, coming maybe out of the cave, or maybe coming into the cave as my reference point. And I was like, if I'm here, I want to be able to see all the different rooms of the campus. And I want to get a variety of some of the mixture of trees that's already there, and maybe little peaks looking back into the suburbs. So view for me was really important, and view from the center was very important. So to translate this, all I did was take, I know that there's a command or a component inside of Grasshopper called isovist. If we hover over isovist, it says it's going to compute an isovist from a location. For those of you that don't know what isovists are, this will probably be a very useful tool for you when you are considering view. They have been kind of popular for a while. Basically, they are like creating a view cone. And you can imagine taking a view from, like, this is just isovist.org. It's a whole society around isovists and spatial analysis tools. And there are some really great articles on using isovists, whether it's Medium or others. But this is a great article, which I will reference for you all for Grasshopper. It just breaks down what it's asking for. And it says, hey, if you move the position of your viewer around, what is the impact of that as a view cone? So there's a great article as to how to use it and how to imagine it being used on meshes for analysis of, like, meshes are really great because they allow you to add a number of different things on. You can get multiple views and then extracting metrics. I'm not going to go deep into this, but the isovist command can be used to measure complexity versus total visibility. This is kind of an interesting way to imagine this. So some really great graphics can also be used to see different people's perspectives and the overlapping view cones that they make. So more and more to dig in here. The great article, former colleague of mine at Autodesk Research, now doing his own thing. For us, isovist just says, give me a sampling plane and origin. Read this as a point. This is the point, the center of the cave that I care about. That's what's being used here for P. Center centroid, site centroid. I'm using just another point container for graphic purposes just to keep this file clean. This is going into my p-value. And then it says, tell me how many samples you want to make. Think of samples in this case as resolution. The more count you have, again, it only wants integer values. The more count you have, the more resolution it has, the less resolution. And it says, tell me where you want the sample radius. I'm just going to show you what this actually looks like. So here's the center, and it's casting rays out from the center to the radius that you tell it to. Again, let's go back to this graphic here. Here's the center, and it's casting rays out, and it's hitting an object. Here again, let's just go back up here. I have a point. It's casting the ray against it. Notice here, there's a little bit of discrepancy between the object and the view cone. That's because of the isovist number of sampling points. If Daniil, in this case, increased this value to, let's say, 400, it wouldn't have some of these trims. But it doesn't really matter too much. You need to decide what is most important for you when doing this. And then finally, it says, what are the obstacles? What do you want me to hit up against? And in this case, I wanted to hit up against the objects of the trimmed buildings. So this came from my resultant curves that were cut by this, but also included this, the full semicircles or circles. And I recycled that geometry and used it to make an isovist. Now, the isovist on its own is just points. It's just going to create a series of points that are intersecting with your obstacles. And the distance from your center viewpoint to each of these. You could use distance perhaps as well. There's ways of recycling each of these. They could be handy. But I just want to take all these points and I want to connect them to make a line so that it graphically looks like a view cone. Now I'm getting closer to that with this, but I realize that if I turn these points off here, what I tried to do when I made this, I made a polyline, and I was like, okay, I think I just want to make a surface from this just for graphics. That's all this really was. Although I could measure the area of it as well. But what I really wanted to do is just make a surface. Whoops. Make a surface from these edges. And what happened is that it said, hey, I cannot make a surface. Something in this curve is not working well. So what I did to solve this little challenge is I baked out this curve inside of Rhino just to be like, hey, what's really going on with this curve? So I'm just middle mouse button, baked it out. And I can click on this curve now. And I'm just going to pull it over here just to show you what it looks like. Here's this curve. So it looks really neat. There's all the points. But check it out. There's a little gap here. And that little gap is what's stopping this from becoming a planar surface. Notice here in Rhino, I'm like, hey, I want to make a surface out of this. Normally, you can do this very easily. You have a circle, and you're like, turn this into a planar surface, and it makes a little surface for you. There's that surface. Doesn't look like much here. Let me go to Arctic. There's that surface. Cool. And I was like, I just want to do the same thing here. But it can't. It can't because it has a little glitch. So what I needed to do is say, close this curve, join this curve together. Now I could do that using a join command. I can try it again now. This was made at an earlier time. These are my curves. I just want to join you together. In this case, it has made a joined curve. Let's see. It made one joined curve. Let me just confirm what that looks like. I'm just going to delete this curve away. I'm going to look at this curve, and I'm going to bake it. Here's this curve. Pull it over here. So it said it was closed, but it's not. So sometimes commands tell you that they're closed. In this, oh, it actually tells you here at the end. If I hover over this, it says, hey, joined curves and individual curves that cannot be joined. I have one locally defined value. It's still a polyline curve. Maybe I could actually take a look at the data coming out of this. And it just says it's a polyline curve. It doesn't even tell me if it's closed. So this is where I needed to say, how can I fix this? I really just want to close this curve up and get to what I want. So what I did is understand that there was a little gap, and I wanted to say, hey, Grasshopper, find for me this curve and tell me where the start and the end is. This is a command called endpoints. It's under the curve ribbon tab. Under analysis, it's analyzing something. And it's trying to tell you, oh, here's another command to tell you if a curve is closed. Handy. In this case, I just wanted it to tell me where I can find the endpoints of the curve. Where even is that? Endpoints, here we go. So the endpoints will find for me a starting point and an endpoint. Again, that was that gap over there. And then I want to close that line. I want to make a line from 2 points, the starting point and the end point, just to fill in that little gap. And then bring both together and join the result. Now, if I bake out this version, just again to show you what's happening here, that gap is gone. And now I can make a planar, oops, I can make a planar surface out of this. Perfect. That's what I'm looking for. Just save these so that you guys have clean files. And save my Grasshopper file. And now I can calculate the length of this curve, knowing that it's closed. And I can add it all up in case they were in separate segments. This may not necessarily be needed. It's just a habit of mine to always add things up in case of anything. I can check what the length is here. It's exactly the same. I did not need to do this because there's only one curve, doesn't need to be added. So forgive this being a duplicative effort. It's just a habit of mine. And I can put this into a number container. And I can tell Galapagos, hey, I want you to take this value here and treat this as the fitness value. I want to maximize this because, again, I'm trying to shoot for diversity and diversity of views, which means the longer this total curve is, the more the view is kind of bouncing around, which is an interpretation of balanced views. So again, it was a qualitative goal that I'm interpreting in this specific way. So the rest of this is anything that I usually put into a blue box is usually just for graphic representation, just to visualize things. But there was my view cone, and I can turn off this red view. I can turn off this view and this one. And here is my result. Here is me calculating 4 different, I'm getting 4 metrics, 4 measures that represent my objectives. And I'm ready at this point to start giving this to a genetic algorithm to start working on it. So that's how to start making evaluators from scratch. So in the end, again, we'll cover how to make these scoring charts for graphics, but you guys can see the file yourselves. This is what it looks like if you need to refer to it. And the objective in the end is to be able to make a script that does something like this. It's allowing control to happen where I can change the positions, the diameters, and I can measure each of these outputs in order to represent my 4 objectives. And in the end, I can feed that to a genetic algorithm to help find for me some results. With the rules, the environment that's there, I can now evolve my design to find great results. So I'm going to stop this video here for today. And yeah, I'll share this very shortly.